The following scenario is hypothetical and presented for educational and entertainment purposes. The first clue that something was wrong with Earth didn't come from a telescope or a satellite. It came from silence. Not the quiet of a still forest or a calm ocean, but the geological kind of silence. No earthquakes rumbling beneath cities, no volcanic plumes rising from restless mountains, no continents drifting across the planet's surface. For billions of years, Earth simply held still. Imagine standing on a world where the ground beneath your feet has never moved. A planet whose crust is a single, unbroken shell. No shifting plates, no grinding boundaries, no recycling of the surface. In our universe, plate tectonics constantly reshapes the planet, driving earthquakes, raising mountain ranges, and recycling carbon deep into the mantle. But in this parallel Earth, that engine never existed. The consequences begin long before humans ever appear. Early in the planet's history, when molten rock cooled and hardened into crust, something unusual happened. Instead of fracturing into drifting plates like the Earth we know, the lithosphere thickened into one massive, rigid layer. Scientists in this alternate timeline would eventually call it a stagnant lid planet, a geological state more similar to Mars or Venus than to our dynamic Earth. Without plate tectonics, the crust never breaks into continents and oceanic plates that wander across the globe. Instead, Earth's surface becomes an enormous geological shield, locked in place for billions of years. At first glance, that might sound stable, even peaceful. No catastrophic subduction zones swallowing oceans, no continental collisions crumpling land into towering mountain chains, no earthquakes shaking cities to rubble. But stability in planetary science is often an illusion. Plate tectonics performs a crucial role in regulating Earth's climate through what scientists call the long-term carbon cycle. On our Earth, carbon dioxide from the atmosphere dissolves in rainwater, reacts with rocks, and eventually gets dragged into the mantle through subduction zones. Later, volcanoes release that carbon back into the atmosphere, completing the cycle over millions of years. Remove tectonics, and that balancing system collapses. Volcanoes still exist in this alternate Earth, but they erupt differently. Instead of forming along plate boundaries like the Pacific Ring of Fire, magma slowly builds beneath the rigid crust until pressure forces it upward in colossal bursts. Imagine eruptions not as frequent but localized events, forming massive volcanic provinces that blanket entire regions with lava. These eruptions are rare, but when they happen, they reshape continents. Without drifting plates to form new mountains through collision, Earth's landscape evolves in a completely different way. The planet becomes dominated by vast plateaus and ancient volcanic shields that slowly erode over hundreds of millions of years. Over time, the surface grows flatter, older, and geologically exhausted. And yet, something even more dramatic begins to unfold in the atmosphere. Because without tectonics recycling carbon, the delicate balance between volcanic emissions and rock weathering starts drifting out of control. For millions of years, the planet appears normal, oceans remain vast, the sky remains blue, life begins in the seas much like it does in our own timeline. But deep within the planet, pressure continues to build beneath that unbroken crust. And eventually, the first planetary-scale eruption is coming. At first, the eruption didn't look like the end of the world. There was no towering volcanic cone, no dramatic explosion captured in a single moment. Instead, it began with a crack, one that stretched across hundreds of kilometers of ancient crust. On a planet without plate tectonics, the crust had grown thick and stubborn over billions of years, trapping enormous reservoirs of heat beneath it. That heat had nowhere to go. No plate boundaries to leak through, no spreading ridges to release pressure gradually. So when the crust finally failed, it failed catastrophically. From orbit, the event would look less like a volcano and more like a glowing wound opening across the surface of the planet. Lava didn't erupt upward, it poured outward. Entire plains transformed into rivers of molten rock spreading across thousands of square kilometers. In geological terms, this kind of event is called a large igneous province, a massive outpouring of basalt capable of reshaping entire continents. On our Earth, these eruptions are rare but real. Events like the Siberian traps or the Deccan traps altered global climate and may have contributed to mass extinctions. But in a world without plate tectonics, they become the planet's primary way of releasing internal heat. And that changes everything. Because instead of steady volcanic activity distributed around the globe, this alternate Earth experiences long ages of quiet, followed by terrifying pulses of planetary volcanism. Imagine tens of thousands of cubic kilometers of lava erupting over a geological blink of an eye. The atmosphere fills with carbon dioxide, sulfur dioxide, and ash. The skies darken. Sulfur aerosols reflect sunlight back into space, triggering sudden global cooling. Oceans lose heat. Photosynthetic life struggles under dim sunlight. But the cooling phase doesn't last forever. As the aerosols settle out of the atmosphere, the carbon dioxide remains, trapping heat and driving the planet toward an intense greenhouse phase. In other words, this Earth swings violently between climatic extremes. First volcanic winter, then runaway warming. Without plate tectonics to regulate carbon over millions of years, these eruptions inject greenhouse gases faster than the planet's natural weathering processes can remove them. Temperatures climb. Polar ice disappears, if it ever existed in the first place. Ocean circulation changes as surface waters warm. But the most important transformation happens on land. Without tectonic collisions forming mountain ranges, there are fewer high elevations for glaciers to carve and fewer fresh rock surfaces exposed for chemical weathering. Mountains on our Earth act like giant climate stabilizers. They provide new minerals that react with carbon dioxide and lock it away. On this stagnant Earth, mountains are rare and ancient. Over time, erosion grinds them down into vast, low plains. Rivers become slow and sprawling. The continents flatten. And as the planet warms, rainfall patterns shift dramatically across these ancient landscapes. Some regions become hyper-arid deserts stretching across thousands of kilometers. Others transform into immense wetlands where water stagnates across flat terrain. It is a world geologically quiet but climatically unstable. And yet, life is incredibly stubborn. In the oceans, microscopic organisms begin adapting to these harsh swings in climate. Some evolve mechanisms to survive volcanic winters. Others thrive during greenhouse periods. Evolution accelerates in unpredictable directions. Eventually, complex life appears, just as it did on our Earth. But here's the twist. The continents on this tectonically silent planet never drift apart and never collide. They remain locked in their original positions for billions of years, which means the geography of life, the migration routes, the climates, the ecosystems, never reshuffles. For evolutionary biology, that single difference changes the entire story of life on Earth. And when the first complex ecosystems finally spread onto land, they will inherit a planet whose continents have been frozen in place since the beginning of time. For hundreds of millions of years, life on land spreads across a planet that barely changes beneath it. In our world, continents drift slowly but relentlessly. Oceans open and close. Land bridges appear and disappear. Entire ecosystems are separated, reunited, and reshaped by the movement of tectonic plates. This constant rearrangement forces species to adapt, migrate, compete, and evolve in new environments. But on this alternate Earth, the map of the world is permanent. The continents never drift apart. No new oceans open. No supercontinents form and break apart in repeating cycles. The geography of the planet becomes a static stage where evolution must play out with the same backdrop for billions of years. At first, this stability seems like a gift to life. Forests spread across enormous uninterrupted land masses. Rivers follow the same ancient paths for hundreds of millions of years. Ecosystems grow vast and complex without being torn apart by shifting continents. Species migrate freely across enormous regions without facing the geographic barriers that shaped evolution on our Earth. But that stability hides a subtle evolutionary trap. On our Earth, isolation is one of the most powerful engines of biodiversity. When continents drift apart or mountains rise, populations become separated. Over time, those isolated groups evolve into entirely new species. Plate tectonics, in a way, acts like a planetary-scale experiment in evolution, continually reshuffling life into new combinations. Without it, speciation slows. Animals and plants spread across enormous uninterrupted habitats. Instead of diversifying into thousands of specialized forms, many species remain genetically connected across continents. Evolution continues, but it moves differently, favoring adaptability over specialization. The biosphere becomes dominated by a smaller number of extremely versatile organisms capable of surviving dramatic climate swings. And those climate swings are growing worse. Remember the planet's unstable carbon cycle. Without tectonic recycling of carbon, greenhouse gases continue to accumulate during each massive volcanic episode. Over tens of millions of years, the atmosphere slowly thickens with carbon dioxide. Global temperatures climb higher than anything seen in human history on our Earth. Oceans warm dramatically. Tropical climates spread toward the poles. Vast regions of the planet become hot, humid, and oxygen-rich. Perfect conditions for enormous biological growth. Forests grow dense and ancient, spreading across low, endless plains. Gigantic wetlands dominate continental interiors where water collects on the flat terrain. The atmosphere becomes thick with oxygen produced by these immense plant systems. And when oxygen levels rise high enough, something remarkable begins to happen. Life starts growing bigger, much bigger. On our Earth, high oxygen levels during the Carboniferous period allowed insects to grow to extraordinary sizes. Dragonflies with wingspans wider than hawks once filled the skies. But those conditions were temporary, eventually disrupted by tectonic shifts and climate change. On this tectonically silent Earth, those conditions persist far longer. Gigantic arthropods dominate the air and forest floors. Amphibian-like creatures grow massive in the endless wetlands. Evolution favors organisms capable of thriving in warm, oxygen-rich environments. But the true rulers of the land emerge later, because eventually vertebrate life begins to experiment with something far more ambitious: fully terrestrial dominance. In a world with stable continents and vast, uninterrupted ecosystems, large predators can spread across entire hemispheres without geographic barriers. Prey species evolve speed, armor, and group behavior to survive. Gigantic herbivores roam ancient plains that have not moved for 1 billion years. The balance of ecosystems becomes enormous, stable, and ancient, almost timeless. But deep below this calm surface, the planet's interior is still restless, because the same stagnant crust that froze the continents in place is still trapping heat inside the mantle. And that heat has been building for over 1 billion years. Eventually, the planet will need to release it again. Not with a single eruption, but with something far more terrifying: a geological event capable of changing the entire surface of the Earth at once. For nearly 1 billion years, the planet holds its breath. Forests stretch across continents that have never moved. Oceans circulate along the same coastlines that existed when complex life first emerged. Species rise, dominate, and fade, but the geography beneath them remains unchanged, a frozen map written in stone. But inside the planet, time is running out. Earth's interior is still hot, still convecting, still trying to release energy. In our world, plate tectonics constantly vents this heat through mid-ocean ridges, volcanic arcs, and spreading seafloors. It is a slow planetary breathing system, quietly regulating the temperature of the mantle. On this Earth, that breathing never existed. Instead, heat accumulates beneath the rigid lithosphere like steam trapped under the lid of a sealed pressure cooker. Mantle plumes, vast columns of superheated rock rising from deep within the planet, push upward again and again, only to be blocked by the thick, unmoving crust. For hundreds of millions of years, the pressure grows. Then one day, the crust begins to flex, not in one place, but everywhere. At first, the changes are subtle. Geologists, if intelligent observers existed to study them, would notice strange patterns in the landscape. Ancient plains begin to bulge upward by hundreds of meters. Entire regions slowly rise as if the planet itself is swelling. Deep underground, mantle plumes are gathering, dozens of them. Because when a planet cannot release heat gradually, it stores the energy until the release becomes catastrophic. The breaking point arrives without warning. Across multiple continents, the crust fractures along enormous radial patterns stretching thousands of kilometers. These are not the narrow rifts of plate boundaries. They are continental-scale ruptures, tearing open the stagnant lid of the planet. And when the crust finally cracks, the mantle answers. Lava floods the surface in volumes the world has never seen before. Imagine not a volcano, but an ocean of magma pouring from the Earth itself. Basalt spreads outward in glowing sheets hundreds of meters thick. Entire ecosystems vanish beneath rivers of fire moving as wide as seas. The atmosphere fills with ash, sulfur, and carbon dioxide at levels beyond anything life has ever experienced. Within decades, the planet enters its first true global volcanic winter. Sunlight dims, temperatures collapse, photosynthesis slows across the planet's forests and wetlands. Food chains begin to fracture, massive herbivores starve, predators soon follow. But this is only the first phase, because after the ash settles, the greenhouse gases remain. Carbon dioxide concentrations skyrocket. Methane released from overheated oceans joins the atmosphere. Within centuries, the planet swings violently in the opposite direction, from freezing darkness to suffocating heat. Oceans begin to lose oxygen, marine ecosystems collapse in expanding dead zones. Coral-like organisms disappear. Massive algal blooms spread across warm seas. On land, forests struggle under extreme heat and unstable rainfall. Entire biomes vanish. This is not just another extinction event. It is the consequence of 1 billion years of geological pressure finally being released all at once. Nearly 80% of complex species disappear in a geological instant, and when the planet finally stabilizes again, the surface of Earth looks almost unrecognizable. New volcanic plateaus cover millions of square kilometers. Ancient forests are gone. The atmosphere is thicker, warmer, and far richer in carbon dioxide than before. But life somehow survives. Small, adaptable organisms endure the chaos, and over millions of years, evolution begins again. Yet this time, the planet itself may have changed in a way that could alter its future forever. Because those massive fractures in the crust didn't just release heat, they weakened the stagnant lid of the planet. And for the first time in Earth's history, the once immovable crust may be starting to move. For the first time in the planet's history, the ground is no longer perfectly still. The massive fractures left behind by the global volcanic catastrophe did more than reshape continents. They fundamentally altered the physics of the planet's crust. For billions of years, Earth existed as a stagnant lid world, a planet sealed under a single rigid shell. But that shell has now been cracked, thinned, and thermally weakened across enormous regions. Deep within the mantle, convection currents are still moving, just as they always have. Hot rock rises, cooler rock sinks. On our Earth, those motions are expressed through drifting plates that slide across the planet's surface. Here, for billions of years, that motion had nowhere to go. But now, the lid is no longer perfect. Across the great volcanic plateaus formed during the planetary eruption, the crust has become thinner and more brittle. The fractures carved into the lithosphere reach deep into the mantle, creating weak zones where motion, once impossible, may finally begin. At first, the movement is microscopic, a few millimeters per year. To any living creature on the surface, it would be completely invisible. But to planetary scientists, if they existed, it would represent one of the most dramatic transformations a world could experience. Because this could be the birth of plate tectonics. For billions of years, Earth existed without the geological engine that defines our own planet. But now the conditions have changed. The crust is fragmented. The mantle beneath it is hotter than ever after releasing ancient heat. Gravitational forces begin pulling newly formed crustal blocks downward where they meet thicker regions. One block begins to sink. It is slow at first, almost hesitant, but gravity is relentless. As the edge of the fractured crust begins descending into the mantle, something extraordinary happens. The sinking slab pulls the rest of the crust with it. For the first time, subduction begins. A true plate boundary is born. Elsewhere across the fractured continents, similar processes start unfolding. Crust stretches along the giant cracks left behind by the planetary eruption. Magma rises through these fissures, forming new ocean basins where lava cools and spreads outward. The surface of the planet, once frozen in place for billions of years, has begun to rearrange itself. Continents that had remained locked together since the birth of life slowly begin drifting apart. New coastlines form. Shallow seas flood low continental interiors. Mountain ranges rise for the first time in unimaginable ages as crustal blocks collide along newly formed boundaries. The planet has awakened geologically, and with it, the rules of evolution change again. The once stable super-ecosystems fracture as continents slowly separate. Species populations that once roamed enormous uninterrupted habitats suddenly find themselves isolated by new oceans and rising mountain chains. Isolation fuels evolution. Within millions of years, biodiversity explodes. New species emerge at astonishing rates as populations adapt to newly separated environments. Climatic systems also stabilize as the long-term carbon cycle finally begins functioning properly. Volcanoes now release carbon gradually instead of catastrophically. Subduction zones pull carbon back into the mantle. Mountain building exposes fresh rock that reacts with atmospheric carbon dioxide. For the first time in the planet's history, the climate begins to regulate itself. Ironically, the most stable Earth imaginable. A world where nothing moved for billions of years turned out to be dangerously unstable. Only through geological chaos did the planet finally evolve the system that makes long-term life possible. And if intelligent observers were to arise on this newly dynamic world studying their planet's past, they might reach a startling conclusion. Their Earth did not begin with plate tectonics like ours did. It had to learn how to move.